When we extend the function to have 3 variables instead of 2, we increase the amount of work we have to do in terms of computation, but we don't fundamentally change anything. Here's an example of a supply function. Before we looked at a demand function, now let's look at a supply function. The quantity supplied is a function of the price of the good or service that's being sold, and the wages paid and the rental rate of capital. Let's compute the price elasticity of supply. So our elasticity of supply, we're going to use the same formula as before. We're going to have P over the function itself, 40, P 0.8, W negative 0.3, and R to the power of negative 0.2. We are going to multiply this by the partial of quantity supplied with respect to price, and that is equal to 40 times 0.8 times price minus to the power of minus 0.2, and then we're going to treat the other variables as constants. We have W to the power of negative 0.3 and R to the power of negative 0.2. And we're going to combine these two together, and when we do that, we get the elasticity. The price elasticity of supply is going to be equal to, after some simplification, 0.8. And so we can compute supply elasticities using the same formula as our demand elasticities. And we see that adding an additional variable had very little impact on our answer. You'll also notice that you may also have noticed that the answer to these supply computation problems is always equal to one of the exponents. The exponent, that's not an accident, that's actually a feature of the Cobb-Douglas function. And so when we're using a Cobb-Douglas function or a power function, the elasticity is equal to the exponent. But that is only true when we're dealing with power functions like the Cobb-Douglas function. Let's try another example. Here we have linear demand. So we've got quantity demanded is a function of price and income. And the equation is 100 minus 2 times P plus 0.1 times I, where P is price, I is income. And the function is going to determine quantity demanded. We're asked to compute our price elasticity of demand, partial derivative of quantity demanded with respect to price, and I get negative 2. Now I can construct my elasticity formula that says I should have price divided by Q, this Q over here, multiplied by the partial derivative of Q with respect to P. And if I sub in some values, I'll have P divided by, no, I'll use by 100 minus 2P plus 0.1 times income. Notice that's I'm using the function itself. And the derivative is negative 2. If I try to simplify this expression, I'm not going to have a lot of luck. In fact, I might just rewrite it as 2P divided by 100 minus 2P plus 0.1 times income. Now I need more information in order to answer the question, and I've been given it over here under task. So now I've been told that the current price is $20 and current household income is 400 units. And now I need to use the values. I need to actually know what the current price is and the current income is if I want to get a single numeric value for my answer. When I do that, I get negative 2 times 20 divided by 100 minus 2 times 20 plus 0.1 times 400. And I get minus 40 divided by 100 minus 40, plus 40, and I get negative 0.4 as my price elasticity of demand. Now I'll let you compute the income elasticity yourself as an exercise. If we move to the last slide, you can see that price elasticity of demand depends on price. So as we move along the demand curve, we're going to have different elasticities. The slope of the demand curve might be the same. It could be, in case of a linear function, it will be constant. The slope will be constant, but the elasticity can still change along the demand curve. So for example, if I told you that the price was 40, you can see that the elasticity is no longer negative 0.4. It actually changes to negative 1.33. And we move from an inelastic part of the demand curve to an elastic part of the demand curve. And so the key idea with linear functions, the slope can be constant along the curve. In this case with linear it will be, but the elasticity changes. So with linear functions, the slope is constant along the curve, but elasticity changes.